Welcome to the Deep Dive. Our mission today, well, it's arguably the biggest one we've ever taken on. We are exploring the alphabet of reality itself. We're zooming right in on what you, the listener, are actually made of.
And we mean that quite literally, everything. The carbon in the device you're listening on, the oxygen you just breathed in, it's all built from atoms that were forged inside stars.
Yeah, and not just any stars. Our sources suggest, based on the chemistry of our solar system, that the stuff making you up right now, your body, your chair, it came from a star that blew up maybe 5 billion years ago.
Right. So if the universe is about 14 billion years old, the material you're made of is what? A third the age of everything? It's pretty mind-blowing.
It really is. And the irony of the sources point this out is that we, this ancient stardust, are now using these massive cutting-edge machines,
The biggest tools ever built.
to figure out where that stardust came from and what holds it together.
Exactly. We've looked at a whole stack of research for this deep dive. It covers everything from, the cosmic history of matter right down to the nitty-gritty physics of particle collisions.
So our job today is to give you the fast track. We're going from the world you see around you down, down, down to the most basic letters in nature's alphabet.
Okay, let's start with scale.
Yeah.
Because it's shocking. Atoms are absolutely everywhere, but they are impossibly tiny. Like one breath, you just inhaled about 1,000,000,000,000,000 oxygen atoms.
Or think about the dot, the period at the end of a sentence in print, that tiny speck, about 100 billion carbon atoms right there. They're just ubiquitous.
So they're tiny, but their history is epic.
Totally monumental. The simplest elements, hydrogen and helium, they're the oldest kids on the block. They formed literally moments after the Big Bang, 14 billion years ago.
But all the other stuff, right? The carbon, oxygen, iron, the things we actually need for, life and planets and tech.
Right, all that heavier stuff had to be cooked up later, inside stars,
Or
through nuclear fusion. That's the cosmic recycling program, basically.
Yeah.
Giant stars live, fuse elements, then explode as supernovae.
And yeah, they seed the next generation of stars and planets with these heavier elements. It's a cycle.
And we're pretty sure about this timeline.
Oh, yeah. The evidence is incredibly strong. Just look around the universe today. What do we see? It's still overwhelmingly made of those first two elements, about 75% hydrogen, which is just protons, and 24% helium.
And that matches the predictions.
Perfectly. It matches exactly what physicists calculate the composition should have been just maybe 3 minutes after the Big Bang. It's amazing validation for the whole model.
Okay, now let's talk structure, because this is where it's really weird, really counterintuitive.
Yeah.
We think of atoms as solid, right? Like tiny marbles.
Nope. It's pretty much the opposite of solid. You've got this tiny, dense, positively charged nucleus right in the middle, and then way, way out you have the negatively charged electrons orbiting.
And in between the nucleus and the electrons.
Mostly. Nothing. Just empty space. The atom is almost entirely void.
But wait, if it's empty space, why does my hand feel solid? Why doesn't it just, pass straight through this desk?
Yeah, that's the million-dollar question. It comes down to forces, not solid stuff. And the scale of the emptiness is just staggering. One source used this great analogy. Imagine that tiny ink dot again.
Okay, the one with 100 billion carbon atoms.
Right. Now imagine you could blow that single dot up, enlarge it until it was the size of the entire Earth. 10,000 kilometers across.
Wow. Okay, huge dot.
Even at that colossal scale, the nucleus of one of those atoms, it would finally be just about visible, maybe the size of a small room compared to the whole planet Earth-sized dot. An atom is about 10 to the minus 10 meters across. The nucleus is 10 to the minus 15 meters. That's 100,000 times smaller.
So it's 99.999 something percent empty space. Then why solidity?
It's the forces, specifically the electromagnetic force. The electrons on the outside of your hand's atoms are repelling the electrons on the outside of the desk's atoms. That force field creates the sensation of solidness. It's pure force interaction, not physical contact between dense bits.
Okay, mind officially bending. Let's drill down even further. You said the nucleus is dense. What's in there? We know electrons seem fundamental, part of a family called leptons. But protons and neutrons in the nucleus, they're made of something smaller.
Exactly. If you could crack open a proton or a neutron, you'd find the real fundamental building blocks as far as we know. You'd find quarks. These are the true alphabet.
Quarks. Okay, what are they like?
Well, there are different types or flavors, but the ones that make up normal matter are called up and down. A proton is made of 2 up quarks and 1 down quark, UUD, gives it a positive charge. A neutron is 1 up and 2 downs, UDD, makes it neutral.
So just 2 types of quarks make up pretty much all the nuclear matter we see.
Pretty much all the stable matter, yeah. But here's the really weird thing about quarks. You can never find one by itself.
What do you mean? Like you can isolate an electron?
Right, but not a quark. They are always found stuck together in groups like the triplets in protons and neutrons. This is called confinement.
Why? What keeps them locked up?
That confinement is actually the key feature of the strong nuclear force. It's the force that glues quarks together. And it behaves, well, very strangely. Unlike gravity or electromagnetism, the strong force gets stronger the farther apart you try to pull the quarks.
Wait, stronger, not weaker with distance.
Exactly. It's like an unbreakable rubber band. If you pump energy in to try and pull two quarks apart, the energy just creates more quarks, which instantly partner up. You can't win.
Huh. So that's how they knew quarks existed, even without seeing one alone, by this bizarre force behavior.
That's a big part of it, yeah. It's indirect evidence, but very compelling.
Okay, so the strong force is one. This seems like a good time to quickly run through the 4 fundamental forces that run the whole show.
Sounds good. We've mentioned 2 already. First, gravity. We experience it all the time, holds planets and galaxies together. But compared to the others, it's incredibly weak, especially at the atomic scale.
Right. Then electromagnetism. This holds the electrons to the nucleus, governs all of chemistry, light.
And it is vastly stronger than gravity at this scale. The sources give a number like 10 to the power of 40 times stronger. It's mediated by massless particles called photons.
An almost unbelievable difference.
Okay.
Number 3 is the strong force we just talked about, the quark glue.
Yep. Mediated by particles called gluons. Super strong, but only acts over incredibly short distances, basically inside the nucleus. It has to overcome the electromagnetic repulsion between all those positive protons crammed together.
And the last one, number 4.
That's the weak nuclear force. Its name is a bit misleading because it's stronger than gravity, but weaker than the other 2. Its main job is to change one type of particle into another, like in radioactive beta decay, it can turn a neutron into a proton.
So it transforms things. Is that important?
Absolutely critical, that neutron to proton change. It's essential for the nuclear fusion that powers the sun. Without the weak force, the sun wouldn't shine. It's mediated by heavy particles, the W and Z bosons, unlike the massless photon.
Okay, so 4 forces, couple of quarks, up, down, electrons. That's the basic kit for everyday matter.
That's the first generation of matter particles, yes. Up quark, down quark, electron, and its partner, the neutrino. That's all you need for stable atoms. But the research shows there are actually 2 more generations of quarks and leptons, heavier, unstable copies.
Like what?
Like charm and strange quarks, top and bottom quarks, and heavier electron-like particles called muons and tarass, each with their own neutrinos. But these guys are super heavy and decay almost instantly. We only see them created in high-energy environments, like particle collisions or cosmic ray impacts.
Which brings us to the next big question. If quarks are confined and all these other particles decay instantly and everything is way too small to see, how on earth do we study any of this? You can't use a microscope.
Nope. Visible light's wavelength is way too big to resolve something as small as a proton, let alone a quark. So we kind of have to cheat. We can't see them directly, but we can smash things together with incredible energy and study the debris.
That's where particle accelerators come in.
Exactly. These aren't small desktop machines. We're talking massive engineering projects. Think of CERN's Large Hadron Collider that's a 27-kilometer ring underground, or linear accelerators stretching for kilometers.
What do? Just accelerate particles really fast?
Basically, yes. They use powerful electric fields to boost particles like protons or electrons to near light speed, and strong magnetic fields to steer them. Then they smash these beams head-on or into a fixed target.
Why? What's the point of the crash?
The collision releases a huge amount of energy in a tiny space. Remember E-mc squared? Energy can turn into mass, into new particles. And the conditions in that collision, the intense heat and density, they actually mimic the conditions of the universe just moments after the Big Bang.
So you're recreating the Big Bang in miniature.
In a way, yeah. For a fraction of a second, you create this state called the quark-gluon plasma. It's like the primordial soup before protons and neutrons even formed, where quarks and gluons were briefly free. Studying how this soup cools and forms particles tells us the fundamental rules.
That's incredible. You build these absolutely enormous machines just to study the tiniest fragments of reality for the briefest moments.
It's driven by pure curiosity, trying to understand the basic laws. But the payoffs have been, well, surprisingly practical.
How so?
One great example from the sources. Managing the sheer amount of data coming out of detectors at CERN, billions of collision events per second, required a new way to share information globally among physicists.
Oh, tell me.
Yeah. That effort led directly to the invention of the World Wide Web. The internet, as we know it, has its roots in particle physics data sharing.
Wow, okay, that's a pretty major spin-off. Anything else?
Oh, absolutely. The supersensitive detectors developed to track the paths of these fleeting particles, especially silicon detectors that can measure positions down to microns. That technology is now fundamental to things like PET scanners and other advanced medical imaging.
So fundamental research really does drive innovation everywhere.
It often does, and those detectors are how we see the results. They don't take photos, but they track the charge, momentum, and energy of everything flying out from the collision point. Even if a particle only travels a hair's breadth before decaying, the detectors can reconstruct its path and properties, letting physicists figure out what was created.
Okay, so we've got the basic alphabet, quarks, leptons, the grammar, four forces,
Uh-huh.
and the tools to study them. And it sounds like we've got it mostly figured out.
Well, yes and no. The standard model, which describes all this, is incredibly successful, but it's definitely incomplete. There are some huge mysteries, big gaping holes in our understanding that are driving all the research today.
Like what? What are the big puzzles?
Mystery number one is probably dark matter. When astronomers look at galaxies and galaxy clusters, they spin too fast. There's not enough visible matter, stars, gas, dust, to provide the gravity needed to hold them together.
So there's missing mass.
A lot of missing mass. About 85–90% of the total mass in the universe seems to be invisible. We call it dark matter because it doesn't seem to interact with light at all. We only know it's there from its gravitational pull.
What could it be?
That's the trillion-dollar question. The leading idea is it's some kind of new, undiscovered particle, probably heavy, slow-moving, and very weakly interacting. Theories like supersymmetry, SUSY, predict partner particles for all the ones we know, and some of those, like maybe a photino or gluino, could be candidates. Finding it is a huge goal for experiments.
Okay, dark matter. What's puzzle number 2?
The antimatter problem. The physics we know, especially EMC squared, suggests the Big Bang should have created equal amounts of matter and antimatter.
Right, matter's opposite twin. And they annihilate each other on contact.
Exactly, turn into pure energy, like gamma rays. So if they were created equally, they should have all canceled each other out in the early universe. We should be left with just a universe full of light. But here we are, made of matter.
So why did matter win? Why is there anything left but energy?
There must have been some tiny asymmetry, some subtle difference in the laws of physics for matter versus antimatter that let a little bit of matter survive. Physicists are searching for this difference, called CP violation, by studying the decays of heavy, unstable particles, particularly things called B mesons. Maybe their decay slightly favors matter production. It's a really tricky measurement.
A tiny imbalance explaining everything. Okay, mystery 3.
This one's about mass itself. Why do particles have the mass they do? And why, for example, are the W and Z bosons, the carriers of the weak force, so heavy, while the photon, carrier of electromagnetism, is massless?
Where does mass actually come from?
The standard model's answer, which was spectacularly confirmed a decade ago, is the Higgs field. This is an energy field that permeates all of space. Particles acquire mass by interacting with this field.
Like wading through cosmic treacle.
Kind of, yeah. Some particles interact strongly with the Higgs field, and they become heavy. Others, like the photon, don't interact at all, so they remain massless. Finding the Higgs boson, the particle associated with this field, at the LHC, was the proof this mechanism is real. But there are still details about why the masses are what they are that we don't fully get.
Right. And the last big puzzle.
Mystery number 4, neutrino mass. For a long time, we thought neutrinos, those ghostly partners of electrons, were massless, like photons. But then experiments designed to count neutrinos coming from the sun kept finding fewer than expected.
The solar neutrino problem.
Exactly. The solution turned out to be something called neutrino oscillation. Neutrinos can actually change type or flavor as they travel. An electron neutrino can morph into a muon or tau neutrino. And the physics says this oscillation is only possible if neutrinos have some mass, even if it's incredibly tiny. We now know they do have mass, but it's very small, and understanding its origin is crucial for cosmology. Hashtag tag outro.
Wow. Okay, that was quite a journey. We went from stardust, literally the ashes of exploding stars from 5 billion years ago.
Yeah.
down through atoms into the nucleus, finding quarks held by the strong force, all governed by just four fundamental interactions.
And we saw how we use these enormous, almost unbelievably complex machines, accelerators, and detectors to probe these tiniest scales by recreating the Big Bang's energy.
All driven by this fundamental curiosity about what reality is made of.
Yeah, and the search just keeps revealing deeper layers and honestly stranger ideas. It's humbling how much we figured out, but also how much is still out there. Like, we understand the standard model pretty well, but it doesn't include gravity properly, it doesn't explain dark matter.
And some of the theories trying to solve those puzzles, like string theory or ideas about dark matter, they hint at things even weirder, right?
Oh, definitely. Some current theories seriously propose the existence of extraspatial dimensions beyond the three we perceive. Tiny, curled-up dimensions that might only be felt by gravity, perhaps.
So the universe we experience might just be, what, a slice or a membrane within a much larger, higher dimensional reality.
That's one of the mind-bending possibilities physicists are exploring. It sounds like science fiction, but it emerges from the mathematics trying to unify the forces and explain things like why gravity is so weak.
Well, that is definitely a provocative thought to end on. The quest to understand the alphabet of reality might just reveal that the book is much, much bigger than we ever imagined.
And that relentless search, just trying to figure things out, keeps spinning off technologies that change our world in unexpected ways.
Absolutely. We hope this deep dive encourages you to keep exploring the fundamental structure of the cosmos. It's a story still very much being written.